Today in the workshop, we'll be working with the I2S protocol. You'll see how we can use inexpensive I2S devices to build digital audio projects with an ESP32. We'll also build an MP3 player and an internet radio. It's sounding pretty good in here today, so welcome to the workshop. Well, hello and welcome to the workshop, and today we are going to be working with the I2S protocol and the ESP32. Now, you may have seen the term I2S on the list of specifications for the ESP32 or the Raspberry Pi or a number of other microcontrollers that support it, and you might not have known what it was. In fact, you might think, well, isn't that just I2C, maybe just a different form of it? Well, it isn't. Indeed, the I2 part does mean the same thing. It means inter-integrated circuit, but that's where the similarity ends, because I2S is a protocol for the transmission and reception of sound, and it can handle 2 channels of digital audio. And so what we're going to do today is we're going to take some I2S peripherals, we're going to take an ESP32 and see how we can get them to work together. But before we do any of that, you're going to need to learn a little bit about digital audio and about the I2S sound protocol. So let's do that right now. I2S is the Inter-Integrated Circuit Sound Protocol. It was developed by Philips Semiconductors in 1986. It was built as a connection standard for digital audio devices and integrated circuits, and was originally for use within the television industry. I2S can control 1 or 2 audio channels of pulse width modulated audio. With I2S, the user specifies the bit level and sample rate, so it can be used for telephone quality signals as well as for super high fidelity. One of the 2 basic units of digital audio is the analog to digital converter. This is a device that converts an analog input signal into a digital output signal. The resolution of the analog to digital converter is determined by the number of bits that it uses. The frequency response of the A to D converter is determined by its sample rate, which must be at least double the highest frequency that you wish to sample. The other fundamental component of digital audio is the digital to analog converter. This converts the digital input signal back into an analog output. It has the same specifications as far as resolution and sample rate go. Let's take a look at the process of delivering digital sound to the consumer. The sound is captured and fed into an amplifier where it appears as an analog signal. This analog signal is fed into an A to D converter and turned into a digital representation of the sound. On the consumer side, the digital signal is fed into a digital to analog converter, which produces an analog output. That analog output is amplified and is delivered to the consumer. In digital audio applications, the analog to digital and digital to analog converter resolutions can vary between 8 and 32 bits. Sample rates can vary between 8 kHz and 192 kHz. As a reference, CD quality audio is 16 bits resolution with a 44.1 kHz sample rate. The digital audio signal is in serial PCM or pulse-coded modulation format. This signal is routed to the different components using I2S. I2S uses a standard 3-wire connection plus a ground connection. There are a couple of optional wires, such as a master clock and multiplex data lines. On the 3-wire bus, the first connection is the continuous serial clock or SCK connection. The WS or word select pin determines whether we are transmitting the left or right channel of audio. And the SD is the serial data, the actual PCM audio data itself. If we examine the waveforms of the I2S bus, we'll see the serial clock is at a constant rate. The serial data is the audio data, and it varies between 0 and 1. Whether that audio data represents the left or the right channel is determined by the word select pin. The clock frequency is determined by multiplying the sample rate by the number of bits per channel and by the number of channels. So for CD quality audio, we would have a sample rate of 44.1 kilohertz multiplied by 16 bits per channel multiplied by 2 channels for a clock frequency of 1.4112 megahertz. If we were just sending a telephone quality signal, our sample rate would be only 8 kilohertz, and we would only require 8 bits per channel, and we'd only need 1 channel. This would result in a clock frequency of 64 kilohertz. An I2S network consists of a single controller device and one or more target devices. The controller produces and controls the system clock. Target devices receive the clock. The controller controls the word select line. In other words, it determines whether the left or right channel is being manipulated. Target devices receive the word select information and act accordingly. Here's a typical application with an audio transmitter and audio receiver device using I2S. The transmitter is our controller and the receiver is our target. So the transmitter is sending the clock, the word select, and the serial data, which is the actual audio that's being transmitted. But things don't have to be configured this way if we don't want to. We can also have our receiver become the controller and our transmitter become the target. In this case, the receiver, as the controller, is providing the clock and the word select information. However, the transmitter is still providing the serial data as it is the source of the music. Another viable configuration is to have both the receiver and transmitter become targets and have an external controller device that provides the clock and the word select information. Again, the serial data is coming from the transmitter because it is the source of the audio. The ESP32 has two I2S peripheral devices. These devices can be configured as either controller or target. They can also be set up as either a transmitter or a receiver. Direct memory access allows the serial data to bypass the ESP32 processor for improved performance. Each of the I2S peripherals is a half-duplex device, so together the ESP32 can perform full duplex. The I2S0 peripheral can route its output directly to the ESP32's internal 8-bit digital-to-analog converter. I2S0 can also transmit pulse density modulation signals. The ESP32 implementation of I2S also supports what's called LCD mode, which is a mode allowing the controls of external cameras and displays using I2S. I2S in the ESP32 can be used for multimedia controllers, music players, telephony, toys and games, professional audio, and a myriad of other applications. So let's put some sound into our projects using I2S and the ESP32. So I've got a little collection of I2S devices to show you. I've got them here on the workbench along with some of the connectors that go along with them. And you can basically divide these devices into two categories. They're either microphones that produce I2S data. They have microphones and analog to digital converters on them. Or they are the opposite end. They take in I2S data and they produce an analog output for a speaker or for headphones. And so they will have a digital to analog converter plus an amplifier on board. Let's take a look at the microphones first. It's these two tiny things here, and if you notice the size of my pen as a reference, you can see just how tiny they are. These little metal squares on here are actually both the microphones and the analog to digital converters, and the output here is going to be on I2S, and you can select whether you want it to be the left or the right channel. These three over here are pretty well the same type of devices. These are the opposite end in which they take in an I2S signal and they produce an analog output to a speaker output. So they've got a digital to analog converter and amplifier on board, and you can strap them to use either the left channel, the right channel, or do a combination of both channels. And this device over here is from Adafruit. It's a stereo DAC, and it's got a stereo headphone microphone jack over here that you can plug into some speakers or into some headphones if you wanted to. And it's got a high quality DAC on it, and again, this is a device that you'd feed I2C to, and it would produce a stereo output from it. So you're going to be seeing a few of these devices in today's experiments, and all in all, just an example of the great selection of I2S devices that you can experiment with. So now that we know more about I2S and digital audio, it's time to get to work with it. And we're going to begin with one of the I2S microphones that I showed you a bit earlier. Now these microphone modules are pretty amazing. They've got a very tiny MEMS microphone on them, and they also have the required analog to digital converter in order to convert this into digital audio, so they're quite easy to use. Now in this experiment, we're just going to use the I2S library that is included when you install the ESP32 board on your Arduino IDE, so we're not going to be using any dedicated libraries, although we will a little bit later on in the video use some dedicated libraries. So let's begin by hooking up our I2S microphone to our ESP32. The I2S microphone that we'll be using today is a very popular module, the INM-P441. Despite its low cost, it has some very impressive specifications, including a 24-bit digital I2S interface. The device has a signal-to-noise ratio of 61 dBA, which is quite impressive. It also has a frequency response of 60 Hz to 15 kHz. Note that on this module, as with most I2S MEMS microphone modules, you actually need to mount it upside down, as there is a hole on the bottom of the printed circuit board, and this is where the sound enters for the microphone. We'll be using the INM-P441 with an ESP32 board. You could use any ESP32 board that you like. I'm showing the WR-over board. If you use a different board, make certain that you wire everything by the GPIO number and not by the actual physical pin number. You could also use different GPIO pins if you wish, as none of them are critical. You would, of course, have the change to sketch to reflect your changes. We'll begin by connecting one of the ESP32 grounds to the ground on the INM-P441. We'll connect the 3.3 volt output of the ESP32 to the VDD pin on the microphone module. The SD line, which is our data line, will be connected to GPIO pin 32. The SCK line, which is the clock line, will be connected to GPIO 33. And the WS line, which is the word select line that determines left from right, is going to be connected to GPIO pin 25. We'll also connect the L/R pin to ground. This sets the microphone to give a left channel output. If you bring this pin high, the output will be on the right channel. And this completes our wiring. Now here's the code that we're going to be using to sample our I2S microphone, and all we're going to be doing with this code is taking the sound in, decoding it, and printing it out to the serial plotter so we can look at the waveforms on the plotter. Now we're not going to use any special library with this. We're going to be using the I2S library that was included with your ESP32 installation in the Arduino IDE. So we called the I2S library right over here, and then here we define the connections we've made to our microphone. Now there's nothing particularly special about these 3 GPIO pins, so if you want to use 3 different ones, you can just change everything accordingly. The ESP32, as you recall, has 2 I2S processors. We're going to be using processor 0, so we define that here, and we define a buffer length that we're going to be using. Now we have 2 functions that we've created, and these functions are just to make configuration of the I2S a little bit easier. This one does all the configuration functions for it, and you can see a number of them buried here in the configuration screen. We're going to be running this in the controller mode, and we're going to be running it as a receiver, a sample rate of 44.1 kilohertz. We're going to be using 16 bits, and we're going to be using only the left channel. Now, something you might want to note, the I2S library has recently changed, and some of the previous functions were degraded. And when they were, some of them stopped working, and you'll find a lot of code that goes with those libraries that fails to compile. And I'll tell you from some experience that if it does fail to compile, it is this line over here that probably is the culprit, because the syntax has changed with the new library. So this is correct for the new library. If you run into any old code that won't compile, you might want to look at that. At any rate, after putting all the configuration data in, we just install that data, and that's the end of that function. We have another function called I2S set pin, and it sets up the pin configuration, and so we just pass it the 3 pin values, and then we do an I2S set pin in order to configure it. And then we'll go into our setup now. Now in the setup, we're going to set up the serial monitor because, of course, we're using the serial plotter, so we do that. And then we set up the I2S, and we can call the 3 functions that we called earlier, the install, the set pin, and then we'll do a start on the I2S port that we have, and that completes our setup. Now we're going to go into the loop, and remember, we're going to try to print this out onto the serial plotter. Now the serial plotter has a dynamic y-axis, and you can't do anything about that, and sometimes it's a bit annoying, including in this particular situation, because what will happen is if we have hardly any sound, the axis will increase in sensitivity so that all we're seeing on it is the noise, and then we suddenly have sound. The axis is going to jump up to a level of about 2, 3, even 4,000. And so in order to steady it, what I've done is I've printed 2 different values, a positive and a negative one, and I'm calling them the range limit. And you can adjust this value over here for range limit. I found 3,000 was pretty good, but you might find a higher or a lower number works, and that'll just kind of lock the range of the serial plotter to make the waveform easier to see. And then after that, we're going to get the business we're out for, the I2S data. We're going to grab that data, and if we get the results, we're going to go and print that data. We'll average it and print it out to our serial plotter, and then we'll do it over and over again. So it's a relatively simple sketch, and it illustrates how to use the I2S library. Let's load it up and take a look at it in action. So here's my setup with the I2S microphone and my ESP32 dev kit. I've got the microphone mounted on a small solderless breadboard, and I'm not sure if you can see it that well, but the microphone is mounted what you might consider to be upside down. In other words, the component sides are facing the solderless breadboard, and that is the correct way of mounting this microphone. There is a hole on the bottom, and that's where the sound is coming in. Now, if you're looking at the serial monitor, you can see my voice right now as I'm speaking, as it's going on the serial monitor. You'll also see a line at the top near 3,000 and one down near negative 3,000, and those are the fixed values that we put there just to hold the serial monitor in place. And so I can actually exceed those values sometimes. Let me just go and clap. I'm going to make a loud noise over here. And I come pretty, yeah, over there I exceeded it a couple of times. So you could play with the 3,000 value, but I found that it was suitable for most applications. Without that, you're going to see this dancing all over the place. But as you can see, we can see the waveforms of my voice on the serial plotter. And so this does seem to indeed work. We are picking up sound in an I2S format and delivering it over to the ESP32, which in turn is translating it and printing it out to our serial plotter. So it does seem to work pretty well. And so using the I2S library that comes with the ESP32 board is a pretty easy way to talk to I2S peripherals, but there are other libraries as well that we can use. Now there's a bit of a story behind my library selection, so I'm going to try to make it brief. It started out back in March when I was actually working on this video because I was planning to bring this video out at the end of March. And it was a Sunday morning, I was working on the video, decided to take a break and see what Andreas had on his channel because he releases his videos on Sunday mornings. And when I went and looked, Andreas had just released a video on using I2S with the ESP32. So I thought to myself, well, I can't release this video next week. It's going to look silly. We have a lot of the same audience, and it's going to look like I'm just copying Andreas, which I certainly wasn't doing. But in Andreas's video, he brought out this excellent library. It's kind of like the Swiss Army knife of libraries for the ESP32 and I2S. Swiss Army knife, Andreas with the Swiss accent. Anyway, this library was wonderful. It had everything. It had equalizers, all kinds of audio devices that you could build with it. But I felt that using the same library he used really wouldn't serve any point because he's already covered it very thoroughly. So I'm using another I2S library today, and the first project that I'm going to be building with this library is an MP3 player. We're just going to take an MP3 file that's on a micro SD card and play it using an I2S amplifier. So let's go and see how we hook that up and then how we code for it. The output of our MP3 player will be provided by an MAX98357A I2S amplifier module. This is a very popular module and it's made by several different manufacturers. The device is a 3-watt Class D amplifier and it has an I2S input. It has a built-in I2S digital to analog converter. It can be configured to use the left, the right channel, or by default a mix of both channels. Now here are the pinouts for this device. The LRC connection would be the I2S WS connection. This is the line that selects whether the left or right channel is being used. The BCLK is the I2S clock line, the SCK line. Now here's where things get a bit confusing. The D-in line is actually the SD line on the I2S bus. This is where the data comes in. It's not to be confused with the other pin labeled SD, which I'll talk about in a moment. The gain pin can use a resistor to set the value of the gain of the amplifier. This pin can also be grounded. The SD line, as I mentioned, is not the data line. Instead, this is how you select the left or right output channel. You use a resistor on this line up to the VCC in order to do this. Now, by default, it is set to a blend of both channels, so if you have no connections, you will get a mono output. GND is, of course, the ground line, and VIN is the power supply line, and this device can take anywhere from 3 to 6 volts DC. For the micro SD card, I didn't want to use just any module, and I chose the Adafruit 254 micro SD module. I chose this device because it is both 3.3 and 5 volt compatible. You'll have to be careful about that because although the micro SDs themselves work on 3.3 volts, most modules are 5 volt modules and will output a 5 volt logic signal, which would be dangerous to the ESP32. One other feature of this device is that it also has an onboard activity LED, so you can tell if it's actually working. Now we'll be connecting both of our modules to an ESP32, and once again I urge you to look at the GPIO numbers and not the physical pin numbers if you're using a different module than I am. Of course, the amplifier will also need a speaker, and any conventional 4 to 8 ohm speaker will work. Note that you can't use a dynamic speaker or feed this into an amplified speaker because the voice coil in the speaker is actually part of the filter circuitry used in the output of the audio amplifier. We'll begin with the wiring of the MAX9357A amplifier module. We'll connect the V-in on this module to the 3.3 volt output on the ESP32. Note that you could also use a 5 volt connection for this and you would get a lot more power from the amplifier if you did. The GND pin is of course connected to one of the ESP32 grounds. We're also going to connect the gain pin to ground. The D-in pin, which is the data in, is connected to GPIO pin 22. BCLK, which is the clock pin, will be connected to GPIO 26, and the LRC, which is the WS line that selects the left or right channel, is connected to GPIO pin 25. And we'll also need to connect our loudspeaker to the module. Depending upon your module, you may have screw terminals for this, or you might just want to solder these wires directly to the board. On the micro SD module, we'll connect the 5V connection to the 3.3 volt line. Note that although it's labeled 5V, this device will also work on 3.3 volts. We'll connect ground to one of the ESP32 grounds. The CLK line will be connected to GPIO pin 19. The DO line, which on some modules may be labeled MISO, is connected to GPIO pin 18. And the DI line, which on some modules could be MOSI, is connected to GPIO pin 23. The CS, or chip select line, is connected to GPIO pin 5. And this completes our wiring. Now here's a sketch for our ESP32i2S SD music player, and the sketch is made quite simple thanks to the ESP32 Audio I2S library that you can grab up on GitHub. And you'll need to grab that as a zip file and install that into your Arduino IDE. Now this library makes it very, very simple to work with I2S, and it kind of hides all of those intricacies that we had to deal with the microphone sketch from you. So all of the things about setting up an I2S connection are dealt with the library. Now we're going to start by including our required libraries, and the audio library is the library in question. We're also including the SD and file system libraries as well because we're using the micro SD card. We'll define our connections to the micro SD card, and we'll also define our I2S connections. Then we create an audio object, which we've done over here, and we can move into our setup. Now in setup, we have to set the CS line on the micro SD card as an output and then set it a high, and that's the chip select line for it, so it knows that it's been selected, because of course the SPI bus can have two different devices on it, and we want to make sure we know that this is the one we're selecting. Now we'll initialize the SPI bus over here for the micro SD card. We'll start our serial port, and then we'll start the micro SD card over here. Now we're going to set up I2S, and as you can see, it's very easy to do with the audio library. We just do set pinout, and we pass to it the parameters of our I2S connection. We're going to set the volume initially. You can play with this level. Don't make it too high because you'll be surprised at how loud it gets. And then we're going to go and open the music file. So we're going to do an audio connect the file system on the SD, and we're going to open up the bensoundclearday.mp3, which is the theme music for the DroneBot Workshop. And then after that, we're just going to go into our loop, and all we do in the loop is play audio. So it's a very simple sketch thanks to this library. Let's load it up and see if we can make some music with it. And so here's my MP3 playing micro SD demonstration, all set up and ready to go. It's got my ESP32, my I2S amplifier, and my micro SD card over here. This is an old speaker from a television that I was scrapping and I took out, and I'm going to use that as my output device. And it's all ready to go. All I need to do is hit the reset button on my ESP32, and we should start everything off again. So let's just do that. And it plays a pretty familiar tune. Now there are no controls on this MP3 player. The only way to stop it is to literally pull the plug. The only way to start the song again is to literally pull the plug. And I have no control over volume, so let me just do that right now. Got a little bit loud, but it is a basic demonstration of how easy it is to take an MP3 file and use it with the audio library to drive an I2S output device. So as we just saw, using the ESP32 I2S audio library really simplifies working with I2S, and it was quite easy to build an MP3 player with it. It is just as easy to build an internet radio to listen to all of the hundreds of internet radio stations that are out there, and that's exactly what we're going to do right now. Now, hooking up the internet radio is very simple because it's exactly the same hookup as the last experiment, minus the micro SD card. So if if you've already got that hooked up, you can just leave it there and ignore the micro SD card. It also opens up the possibility of building a device that can play both MP3s and listen to the internet radio. And so you could work on that as well using the code that we're about to present. So let's go and take a look at that code, and then we'll hook up our internet radio. Like I said, our internet radio wiring is identical to that of our MP3 project, minus the micro SD card. If you've already wired up the micro SD card, you could just keep it there. It's not going to do any harm. Otherwise, you could just remove it from that circuit. And so now let's take a look at some of the code that we're going to use in order to make our internet radio work. So here's the sketch that we're going to be using for our simple internet radio demo, and once again the sketch has been simplified by the use of the ESP32 Audio I2S library that you need to download from GitHub as a zip file and install in your Arduino IDE. We'll start off by including the required libraries, including the Wi-Fi library and the audio library that we just spoke of. And then we'll define our I2S connections, and it's to these 3 GPIO pins. If for some reason you want to use different pins, just change the sketch accordingly. Then we can go and create an object for our audio. We do that here. We have a couple of variables also to hold the network credentials, so our network SSID and our network password. And then we'll jump into the setup. In the setup, we'll start our serial monitor. We'll start our Wi-Fi in station mode. We will begin it by passing the password and the SSID to it. Assuming that we have connected, we're going to print that out to the serial monitor, including our local IP address, and then we'll connect the I2S amplifier module, and we just use set pinout with the audio library and pass it the 3 connections. We're going to set the volume right now, and don't make this too high a number. When you start off, you can always play with it. I use 10, and then we have to connect to an internet radio station. I've got a number of different ones that you can connect to over here. I've unremarked one of them. If you find that they aren't working very well, you can maybe just try a different one. And then we go into the loop, and the loop is very simple. It's like the loop that we had in our SD player. We just do an audio loop, and it just simply plays. Now, some extra functions we've added down here, these are kind of optional, but they will print out to the serial monitor, is some status functions for audio, and there's a whole bunch of different statuses we can play. We can play the title, we can play some stream info. There's a number of pieces of information that we can put up on the serial monitor, and you can pick and choose from these. You don't necessarily need to use all of them, but it's fun to put them there. And so let's load this up to our ESP32 and see if we can listen to some music with our internet radio. Okay, so I'm playing my internet radio right now, and if you take a look at the serial monitor, you can see I've got a whole bunch of information about what's playing right now, including the fact that I'm playing a classic Queen song, Bohemian Rhapsody. However, you're probably noting that you can't hear it at the moment, and the reason for that is simple enough. If you look over here, I've disconnected my speaker. And unfortunately, the reason I've done that is because of YouTube copyright rules. I can't actually play you Bohemian Rhapsody right now because this video would be flagged as a copyright violation. So you'll just have to take my word for it. You can see now it's flipped over to yet another classic song, Santana's Black Magic Woman. So we got some great music going here on our internet radio, which we sadly can't hear at the moment. But you'll have to take my word for it that as soon as I connect this speaker up, it will be filling the room with music right now. And it does seem to work pretty well. One thing I have noticed, though, is when you start off, sometimes you need to reset a few times occasionally to get a connection, and that sort of depends on the internet radio station as well, and that issue may indeed be an issue on the other end about the maximum number of connections or something that it can accept. But otherwise, as you can see, with an ESP32 and an I2S amplifier, we can build a pretty effective internet radio. Now, the experiment that we're going to do to finish off the video ended up changing a little bit, and it was because of an accident I had over here. I'm still not quite sure how the accident happened. I wanted to show you how we could give both a stereo output and add a volume control to these circuits, because stereo output obviously would make the music sound better, and a volume control is a pretty essential thing for any audio device. And so I was going to do that using the MP3 player, because of course with the MP3 player I can play you some music that doesn't violate YouTube's copyright rules, and we won't have any problems with the video. Well, I had it wired up and was working with it, and then I ejected my micro SD card, and when I went to put it back in, it wouldn't go in. It kept popping out, and I have no idea why. Nothing physically happened to the card reader. So I put it under a magnifying glass, found a little tab on it, and used a jeweler's screwdriver to bend the tab in a bit, and now the card does latch, but it doesn't seem to work properly. I get intermittent data out of it, so I have no idea what happened to my micro SD card, but it kind of messed up the last demo, and it also delayed the release of this video, for which I apologize. So I've reworked it with the internet radio, and of course that's going to make it a little bit more difficult to demonstrate because of the copyright issues, but I'll just try to do it really quickly. And so what I've done is I've changed our internet radio to have a stereo output and to also have a much needed volume control. Now for the stereo output, we will of course be using two I2S amplifier modules, and in order to use these modules we're going to have to strap one for the left channel and one for the right channel. So let me show you how you do that, then I'll show you how we wire everything up and code our stereo internet radio. Now, in order to create a stereo output, we'll be using two Max 98 357A amplifier modules, and they need to be set to either only the left channel or only the right channel. And you do that on most of these modules by using the SD pin. Now, as I discussed earlier, SD is not the serial data pin, that is the D-in pin. This is the pin whose voltage level determines the output mode of the amplifier. When this pin is grounded or set to 0 volts, the amplifier will have no output at all, so you could use this as a form of a mute control if you wish. When the voltage level on SD lies between 0.16 and 0.77 volts DC, then you will get a stereo average or mono signal out of the amplifier. This is the default mode because there's an internal pull-down resistor on the board that maintains this voltage level. You can use a pull-up resistor to the V-in order to get the voltage higher, and if you set it between 0.77 and 1.4 volts, the amplifier will output the right channel. If you make the voltage higher than 1.4 volts, it will output the left channel. Now, if you happen to have a SparkFun implementation of this module, it's a lot easier. There's a jumper on the bottom that is there by default for mono, and you can cut that jumper and then look above it at a couple of traces. There is a center trace and two marked as L and R. You'll just need a blob of solder or some other way of shorting the traces, so you can set this for either the left or right output accordingly. The hookup for our stereo radio is going to be very similar to that of the mono one, except of course we're going to have two amplifiers. However, one change I'm making is instead of powering this with the 3.3 volt output, I'm now powering it with the 5 volt DC output. Note that the 5 volt pin on the ESP32 is both an input and an output. If you're powering this with a micro USB, then you'll get a 5 volt output here. Otherwise, you'll be applying 5 volts here in order to power the ESP32. I'm using 5 volts instead of the 3.3 volts because I feel that the 3.3 volt regulator on board the ESP32 is going to be overly taxed if it's trying to drive two amplifiers that can each output 3 watts. Plus, we'll get a little bit more volume this way. We're going to add a second amplifier board, and we're going to connect it exactly the same as the first one, so everything is in parallel. Note that you'll need to have already strapped your board for the right and the left channel using whatever method your board uses, as we just discussed. Also note that when you're wiring up the speakers, you should try to wire them in phase. In other words, connect the positive to the same terminal on each speaker. That way you'll get better stereo sound. For a volume control, we're going to be using a potentiometer, and the value is not critical. I used a 10K linear pot. Now, you might think that an audio taper pot would do a better job over here, but the actual tapering is going to be done in software, so a linear taper pot will be just fine. We're going to connect one side of the pot to one of the grounds on the ESP32. The center lead or wiper of the pot will be connected to GPIO pin 39. This is also analog to digital converter 03. And the other end of the pot will be connected to the 3.3 volt output. It is very important that you use the 3.3 volt output and not the 5 volt output. And that's all there is to the wiring for our stereo radio. Now let's go and take a look at the code modifications we need to make in order to use our volume control. Now here's the sketch for our internet radio with the volume control and stereo output. And actually the sketch has nothing to do with the fact that it has stereo output. That has to do with the way that we strap our amplifier modules. And you could have received stereo output from our previous sketch. So this sketch really just shows the addition of the volume control. Now we're going to start off by including the same libraries we've always included in these sketches, and then we're going to define our I2S connections, and now we're going to define the connection that we have to the potentiometer that we're using as a volume control. Now we're using analog to digital converter number 3, which is the same as GPIO pin 39, so we define this as a 39, and you could use a different ADC providing you kept it within the same group. There are a couple of groups of ADCs on the ESP32, and the first group is where you need to have this control because the second group is not available when you're using Wi-Fi. Now we define an integer that represents our volume level. This can be a number between 0 for no volume and 20 for full volume, and I've defined it in the middle as being 10. We create an audio object and get our Wi-Fi credentials, so you'll need to substitute your own credentials in over here, of course. Now we go into the setup, which is identical to what it was for our previous internet radio. We start our serial monitor, we'll set up our Wi-Fi in station mode and print the connection information to the serial monitor. We will connect to our I2S amplifier module, and now we'll set the volume to the level we previously defined, which was 10, and connect to an internet radio station. And once again, I've got a number of different ones you can choose from over here. And then we go into the loop, and this is where the real change for the volume control addition is made. We run the audio player as we did before, and now we go and get the volume level. So we do an analog read on the volume control, and then we map that to a level from 0 to 4095, and we bring that to a level of 0 to 20, and we assign that to the variable volume, and then we set the volume using that variable, and we just go back through the loop again. So it's a pretty simple addition. Now after that, we have the same status functions we did before, and this will just print out some status functions out to the serial monitor. So a very simple change to our sketch. Let's load it up and check it out. So here's my stereo internet radio wired up on the solderless breadboard, and you can see the two speakers I've got over here, the two that I salvaged out of my television. Now the amplifier modules I used are over here, and these are the SparkFun modules. And of course the SparkFun modules were very easy to use because all you need to do is cut a jumper on the bottom and then strap it for either the left or the right channel. Otherwise you're going to need to use a pull-up resistor on the SD pin as I showed you earlier, and I would suggest if you're going to do that to use something like a 100K pot on that pin, tie it up to the 5 volt line or the V in, and then adjust the pot until you've got the right voltage level for left or right channel respectively. After that you could just leave the pot in, or you could replace it with a fixed resistor if you wished. Now here of course is my volume control on my ESP32, and it's running right now. It runs very well, but of course, playing music is difficult because of copyright violations. I'm going to see if maybe we can do this very, very quickly, and hopefully that won't flag it on YouTube. So, and we do have level, and it goes up when I turn the control over here. And hopefully we won't be in violation for that Queen song over there that was playing in the background. But you could make the same modifications to the MP3 player. Had I not somehow damaged my micro SD card, I would have demoed with that instead. And as you can see from the code, adding a volume control was a very simple thing to do, and it really makes the internet radio a lot more practical. All right, well, that pretty well wraps up our look at I2S for today. I hope that you enjoyed it, and I hope it's opened your eyes up to the fact that we can use the I2S protocol to build audio devices with our ESP32. Now, if you want some more information about I2S, or if you'd like to grab the code that I used today, you'll find that, of course, on the article that accompanies this video on the DronebotWorkshop.com website. And there is a link below the video right to that article. And while you're on the website, if you haven't yet, please sign up for my newsletter. No, it's not a spam letter. It's just something I send out occasionally, and I've been a little lax about sending it out lately, but I will be sending out one soon. And it's free to subscribe, and it just lets you know what's going on here in the workshop. And also, if you'd like to discuss this a little bit more, if you want a little bit more information about I2S, or you're having problems with one of the sketches, best place to reach me is on the DroneBot Workshop forum. The forum, of course, is free to join, and it's full of like-minded individuals who love working with electronics and who can help you out with your project, or would just like to hear about your project. So sign up for the forum if you haven't done that yet. And while you're in a signing up mood, if you haven't, please subscribe to the YouTube channel. It's very easy to do. You just need to click the red subscribe button, and also click that bell notification. And assuming that you've enabled notifications on your YouTube, you'll get notified every time I make a new video. So until we meet the next time, please take care of yourself, please stay safe, and I will see you again very soon here in the DroneBot Workshop. Goodbye for now.